All right, let's go over right-hand rules number 1 and 2, and then we'll take a look at number 3, which is kind of interesting. Now, in right-hand rule number 1, we have a current carrying wire, and we're concerned with the direction of the magnetic field around it. And it's quite simple. You point your finger in the direction of the current is flowing, I've indicated from positive to negative, and also with an arrow. And you curl your hands. And over here, on this side of the wire, they go into the board, wrap around, and they come out of the board right here. And so we've represented that with X's indicating into the surface and O's indicating out of the surface. Now, when you sketch this kind of thing, you need to get the direction of all the relevant vectors. So we need to know what the direction of the field is, which we indicate by B, direction of the current, or the velocity of a charged particle, which we indicate in that way. And then, spatially, for example, if we want to know the strength of the field at a distance r at point A here, we'd simply use our formula. So that's number 1. And remember, that's the field generated by the wire. So because this field is generated by the wire, it does not act on the wire itself. Because it takes two objects to exert a force. Now, right-hand rule number 2 is concerned with loops of wire or a solenoid. And remember, loops of wire, just any number of loops of wire. A solenoid is an ideal term for something whose length is much larger than the diameter. But in either case, we're going to indicate the direction of current. I'm going to put a positive and a negative terminal here, and we can see the current is going to loop like that physically around it. So our right-hand rule simply says, curl your hands in the direction that the current is looping physically, and your thumb points to the north pole of that electromagnet. So it would be north and south, and the field goes in loops around like that. Now, the third right-hand rule is concerned with what happens if we take that current carrying wire from rule number 1 and we put it in an external magnetic field. In other words, a magnetic field generated by something else. Now, because we have 2 objects with 2 separate magnetic fields, we will get a force exerted. In right-hand rule number 3, if we have a current carrying wire, say like this, so that the current is going in this direction, that's going to generate a field, right? And it would generate a field coming out here and in here. But let's say we impose an external magnetic field on it. We'll call that B. Let's say the field is going into the board. Remember, this is not the field generated by the wire, because that would be an X on one side and an O on the other side. So this wire is sitting in this magnetic field. In order to find the force exerted on it, there's a couple different versions of this right-hand rule. Your book's version is to point your fingers in the direction of the current, and the field is going in, so you sweep your fingers toward the field, and your thumb points in the direction of the force. That indicates that we would have a force upward on that wire, right, all along the wire. Right? Now, a second version, which I prefer, is that you take your fingers and you point them in the direction of the field, and you point your thumb in the direction of the current, and the force comes out of your palm. But that gives us the same result, so you can use either one. Now, to determine the magnitude of that force, that's going to depend on how much wire is in the field and also the strength of the field. And so the force is going to equal the external magnetic field times the current in the wire times the length of wire that's in the field. And magnetic field is newtons per Tesla. and current times, and so the force is in newtons. Now, your book has a second version of this. What I want you to notice here is that IL is going to have units of coulombs per second times meters. If we rearrange those numbers, we get coulombs times meters per second. So a second version of this is to say force equals charge times velocity times the strength of the field. Your book also deals with angles other than 90 degrees. Most of our examples will have the current or the velocity at 90 degrees to the field. In that case, there's another term, sine of theta. And if the motion of the charge or the current is 90 degrees to the field, sine of 90 equals 1, and you get full strength. As the motion of the charge gets closer and closer to the direction of the field, the strength drops. And for example, if we had, let's say we indicate a field, we have a big South Pole magnet here, and a North Pole magnet here. The field between them would be relatively uniform in that direction. Now, if we placed a current carrying wire, right, like that, we put the positive terminal here and negative here so that the current is going like that, and we apply our right-hand rule. Fingers in the direction, curl towards the field, the force would be coming out of the page, so it would be exerting a force out of the page on that. Now, if we turned that, oriented that wire so that it was like this, and the current was going in the direction of the field, in that case theta would be 0, and the force exerted, we can also apply the same sine theta up here. Because theta is 0 and the sine of theta is 0, the force exerted on that would be 0 if it's parallel to the field. So that's the minimum, and then as you rotate, get more and more of an angle with the field, you get more and more force till a maximum at 90. Now let's do a couple examples. And these are from your notes. Oops. Let's say that we have a 0.5 kilometer length of power line carrying 25,000 amps of current, and it's carrying that from some kind of a power generating station due east to New York. What is the force exerted by the Earth's magnetic field on the wire? So let's sketch our situation first. Okay, so we have a length of power line, right? And we have a current traveling east, right? We'll call that east. And we know that the Earth's magnetic field is north. Call that B of the Earth. And what we're doing right now is we're looking down on top of this from up above, and we're seeing the current traveling to the east and the magnetic field of the Earth in that direction. In that case, if we move our fingers in the direction of the current and we wrap our fingers in the direction of the field, we find that the force is coming out of the page. And using the alternate method, thumb in the direction of the current, force, the field in the direction of the fingers, force comes out of the palm. Both methods tell us that this force is coming out of the page. Because we're looking down on that, that means it's an upward force. Now let's find the magnitude of the force. The force is going to equal B of the Earth times 25,000 amps times 500 meters, which is 1/2 of a kilometer. Now we know that B of the Earth is approximately 5 times 10 to the minus 5th Tesla. And we can see that the angle between the current carrying wire and the field is 90 degrees, so we'll have a sine of theta, or sine of 90 equals 1. So the force is going to equal 5 times 10 to the minus 5th times that. And let's do that real quick. Sorry, I have to use my phone.